हो सर नहीं नहीं बघितलं सगळं झालं की okay, welcome to the class. So in the previous class we were discussing about the second order system. A standard second order system is derived from any general second order system, and it has to be brought to a what is known as a standard form. A standard form of a second order system is always represented as omega n square divided by s square plus 2 zeta omega n into s plus omega n square. So if you see the denominator, it will consist of the second order equation because it is highest power of s is 2. So when it has the denominator equation, if you find out the roots of that equation, there will be two roots by using the formula minus b plus or minus under root of b square minus 2ac by 2a formula. There are three possibilities. When zeta less than 1, the roots are complex conjugate because it is, I have to take j outside because under root quantity will be negative. Root of minus 1 is j, I have taken it outside. So the two roots are minus zeta omega n plus omega n into j into root of 1 minus zeta square, that is first root. Second root is minus zeta omega n minus j omega n into root of 1 minus zeta square. That is when zeta is less than 1. When zeta is equal to 1, then both the roots will be equal to minus omega n. And when zeta is greater than 1, that is called as overdamped system. In that case, the roots are minus zeta omega n plus omega n into root of zeta square minus 1 and minus zeta omega n minus omega n into root of zeta square minus 1. After that, now once these roots are formed, now there are three cases. One, underdamped. Second, critically damped, that is zeta is equal to 1. And third, overdamped, when zeta is greater than 1. If you see the first case, now we'll subject this system to a step input, ramp input, and impulse input. In that case, first one is step input, r of t is equal to 1 upon s. Then in that case, if you see the two roots are, first root s1 minus zeta omega n plus j omega d. I have replaced omega d. Omega d is called as damped frequency of vibration, which is given by omega n into root of 1 minus zeta square. So every time writing down omega n into root of 1 minus zeta square, instead of that I am writing it as omega d. So one is with plus omega d, one is with another minus omega d. So here the value of omega d is written omega n into root of 1 minus zeta square. So the two roots are omega n square divided by s into s plus 1, s1, s plus s2. S1 and s2 values are here, and s is because of this. Now once again you have to find out the partial fractions. There are three partial fractions now: a upon s, b upon s plus s1, and c or b star, because s plus s1 and s plus s2 are not two separate things because they are complex conjugate. So whatever is the value of b, same thing will be value of b star, only with negative sign. So only two partial fractions have to be found out. The third partial fraction is same as the second one, that is b with negative sign. That's all. So if you do that, here after finding out the partial fractions, see here, this is the partial fractions a, b, and B star. So this, by usual method, if you evaluate, you will get this derivation, and further it will come to this is not correct. Finally, you will get this as the answer, that is 1 minus e to the power minus zeta omega n into t upon root of 1 minus zeta square into sine phi into cos omega d and plus cos phi into sine omega d into t. So here you can find out from the equation where cos phi is zeta, whereas sin phi is root of 1 minus zeta square, and tan phi is equal to root of 1 minus zeta square divided by zeta. So here you will get the final answer in this form, as well as the same can be expressed in this form also. That is 1 minus e to the power minus zeta omega n into t divided by root of 1 minus zeta square. So this is cos A sin B sin A cos B. That can be written as sin A plus B, that is sin omega d into t plus phi. So this is the output of a second order system subjected to unit step input. See, other derivations are not very commonly asked. So only this derivation you have to prepare. Other derivations you will get it from the book. Try to prepare. That is, you will get for step input, there are 3 derivations. One for underdamped case, which I have done. One for critically damped case, and one for overdamped case, that you have to do it from the book. Similarly, for ramp input also, underdamped, critically damped, overdamped, 3 derivations. And for impulse also, underdamped, critically damped, overdamped. So this derivations, it is not possible to do it in the class. You will get it in number of books, including Ganesh Rao and that another, which one? Nagaraj Gopal. Nagaraj Gopal, he has given only equations. He has not given the derivations. Then another, that Anand Natarajan, that book also is given to you. So refer to that and prepare the derivation. Sometimes these derivations are asked for 5 to 10 months. But most of the time in the exam, if you see the old question papers for VTU as well as GIT, you will find most of the derivations are for first order system and second order only underdamped case with unit step input. So this is what is the derivation. So the complete derivation is given here, this same underdamped case, and then simple examples. Step response of underdamped system. See here, this is our underdamped system, second order underdamped system. For the step input, this is what is the equation. Suppose if zeta, if you substitute as 0.1, damping ratio 0.1, and natural frequency of vibration omega n is is equal to 3, in that case, the response is like this. See here. So it is a step input, unit step input. That means the input is exactly 1. It is the mean value you can see here. And the output response for underdamped system, it overshoots initially. It goes up beyond 1, then comes down, then once again goes up and keeps on oscillating for some amount of time. And finally, it will, when time t is equal to infinity, it will become equal to 1 or equal to input. So second case, see here, If zeta is now increased to 0.5 from 0.1, same, see here, it has oscillations have considerably decreased, and within 2-3 oscillations it will stabilize. Then zeta 0.9 and omega n 3 only, same. See, the oscillations have further gone down. So this is the 3D view of those oscillations where the values are written below. This is not very important, just to visualize the things it is given. Then for critically damped case, when zeta is equal to 1, so the equation becomes like this. Because the two roots are same here, both the roots are minus omega n only. So s plus omega n whole square, the roots are step input. Once again, if you find out the partial fractions method, if you evaluate by usual method, the output you will find out equal to 1 minus 1 plus omega n into t into e to the power minus zeta omega n into t for t greater than or equal to 0. Then overdamped case. So here earlier it was j was there, now j is not there, and 1 minus zeta square was there, now zeta square minus 1 is there. So the two roots are s1, s2, just like underdamped case, the two roots only values have changed. So if you evaluate by the similar method, you will find the output equation like this. So finally, the output equation is something like this, 1 minus this much. These are the three derivations for underdamped case, critically damped case, and overdamped case for second order system subjected to unit step input. So the output graph is something like this. So if zeta is 0, the oscillations will continue for infinite amount of time as zeta goes on increasing. But if it is below 1, the oscillations will be there. As the zeta approaches 1, the oscillations will die down. When zeta is equal to 1, there will be no oscillations and it behaves more or less like a first order system. Whereas if the zeta goes on increasing, the output becomes very slow and very sluggish. See here, zeta 1 is this one, zeta 2 is very slow, zeta 3 is further slower, and it will take longer time to settle. Only thing is oscillations will not be there. These are the three derivations for second order system subjected to unit step input, underdamped, critically damped, and overdamped case. Now, most of the things are related to underdamped system. Underdamped system response is more crucial because most of the components, crucial components used are underdamped. Example, the suspension system of a car. One of the most commonly used system is underdamped system. And for second order underdamped system is example of that is a suspension system in the car where it is a spring mass damper system. And as we have seen in the previous class, the spring mass damper system is second order system. So here if you see the details, if the zeta value is less than 1, underdamped case output, if the input is 1 unit, the output actually overshoots and then it keeps on oscillating and further stabilize, and it will finally reach equal to 1, that is equal to input, when time t is infinity. So it is not possible to wait up to infinity, so we'll put some limit. So if the output reaches within that tolerance band, that is called as settling time. So there are some definitions you can see here. One definition is rise time, second definition is peak time, and third one is settling time, and fourth one is peak overshoot. These are the four important parameters which have to be measured for second order underdamped system. See here, as per the definition, rise time, see here you can see a small one, that is TR. That is a rise time. The rise time as per the definition for underdamped system is, it is time required for the system response to reach equal to input in the first attempt. In the first attempt. That means, as you see here, as the time passes, the output goes on increasing and it becomes equal to input, that is 1, and then further goes up. So it is time taken by the response to reach equal to input in the first attempt, because there are number of attempts. It will keep on oscillating. Here it will reach 1, here also it will reach 1, here also it will reach 1, here also it will reach 1. Not these instances. The instance is first instance. That is, when first time it reaches equal to 1, that is called as the rise time. That is, as per the definition, rise time is time required for the underdamped system to reach equal to input in the first attempt. So that is called as rise time. Then second important parameter is peak time, TP. You can see here TP is there. So it is time taken by the system response to reach equal to the peak of the response. Peak means the first peak will be the highest peak. Further peaks will be smaller. You can see number of times the peaks will occur, but these peaks will go on reducing. If zeta is equal to 1, then peaks will be same. That will be continuously, it will be oscillating only. It will never reach equal to 0. But here, what happens is, here it will reach the peak. The highest peak, time taken to reach the highest peak is called as peak time. That is, it is time taken by the system response to reach the peak value, peak of the response, or the maximum value of the response is called as peak time. Then the next one is settling time. You can see here, this is a TS is written, settling time. It is time taken by the system response to reach within a tolerance band. There are two tolerance bands provided, 3% tolerance and 5% tolerance. 3% tolerance means 5% tolerance means it should oscillate between 0.95 to 1.05. So 5% above 1, 5% below 1. That is 1.05 to 0.95. That is time taken to reach within that band is called as peak time. And there is another definition, 3% tolerance band. 3% means the 3% tolerance band will be further away, because that peak time will be more. Time taken to reach within the 3% tolerance band will be more than 5% tolerance band. And for 3% tolerance band means the system response should oscillate between 3% above 1 or 3% below 1. 3% above 1 means 1.03. 3% below 1 is 0.97. So if it starts oscillating between 0.97 and 1.03, it is called as 3% tolerance band settling time. Then last parameter is peak overshoot. You can see here, it is not time. It is the maximum value above the mean value. Mean is 1. So the distance between the mean value and the maximum value, this distance is called as peak overshoot. So it will be expressed in percentage or in a fraction. It is either expressed in percentage or in a fraction. So for these, there will be 4 derivations. One, rise time. Another one is peak time. Third one is peak overshoot. And fourth one will be settling time. These 4 derivations we have to do. Those 4 derivations we can see now. Okay. See here, this is a rise time derivation. Here the system output I have taken. This is the equation for the output, 1 minus this one. Now, rise time means, at rise time, it is time taken by the system response to reach equal to input in the first attempt. So for input is 1. So output, first time when the output becomes 1, that you have to find out. So CTR is 1. So this is 1. If this is 1 means this remaining part, this is 1 minus something is there. This part should be 0. I have put that part equal to 0. That is e to the power minus zeta omega n into t divided by root of 1 minus zeta square into sine omega d into tr plus phi should be equal to 0. That means, since what happens is, if the zeta is less than 1 always, so denominator cannot be 0. Similarly, in the numerator, e to the power uh, cannot be 0 because it will become 0 when tr becomes infinity. When tr becomes infinity, then only it is possible. So that tr cannot be infinity. So naturally this cannot be 0. So naturally what happens is sine omega d into tr plus phi should be 0, or sine omega d into tr plus phi should be some multiple of pi. So because sine can be 0 only when it is 0, 180, 360 or so on, or pi, 2 pi, 3 pi, or in general up to n pi. So number of times it will become 0. So in the first attempt means when it becomes equal to pi. So if you put omega d into tr plus phi is equal to pi. So n is 1. That is in the first attempt. Second attempt, third attempt, we are not bothered. So n pi means 1 pi. So if you put that equal to this much, then tr can be found out by equation pi minus phi divided by omega d, or pi minus phi divided by omega d value I have put, or tr can be equal to pi minus phi divided by this. So where phi is, what is phi value? We have already substituted earlier. Phi is tan inverse of root of 1 minus zeta square divided by zeta. So phi is root of 1 minus zeta square divided by zeta. See here. This is what is the value of phi. So you substitute here and you will get it. Remember one thing. Here, see, you have to see the units. So TR is time. You should get the unit as time. That is possible because see here, what is the unit of omega n, natural frequency of vibration? It is radians per second. So it is radians per second means radian comes in the denominator, seconds go in the numerator. Whereas this root of 1 minus zeta square is the number. It doesn't have any unit because zeta is damping ratio. Ratio doesn't have any unit. So here the second comes in the numerator, whereas radian comes in the denominator. Then pi and phi should be in radians. So pi is in radians and phi should be also is a radians, because what is the value of phi? It is tan inverse. So tan, whatever tan inverse you take, you should not keep your calculator in degree position, but you have to keep it in radian position, because in the numerator you require radians. So pi is already in radians, phi should also be in radians. That divided by radians per second, radian cancels, second goes to the numerator, so the units will match. This care you have to take. Then next derivation. So rise time. Next derivation, rise time. This graph is shown here. You can see. Then equation for peak time. So to evaluate peak time, what you have to do is, peak means what? Maximum value. How you find out the maximum value of any equation? You have to differentiate that equation and put it equal to 0. You will get two values, one maximum value, one minimum value. So forget about the minimum value. To get the maximum value, what I will do is differentiate the equation of output, that is C, equal to 1 minus e to the power whatever this equation is there. That equation I differentiate with respect to t. If I differentiate that with respect to t, the after differentiation, see here, this is one term and this is second term. So you have to differentiate by using u into v method. Differentiation of u into v plus differentiation of v into u. By that method, if you differentiate, you will get finally the answer like this. So you will finally get the answer like this. That means finally in this case you will get omega sine omega d into Tp is equal to 0, or sine omega d into Tp should be, if the sine has to be 0 means once again 0, pi, 2 pi, 3 pi, so on. So 0 you cannot take, that is peak value cannot be 0. So the next once again you put it equal to pi, that is omega d into Tp is equal to pi, or Tp is equal to pi divided by omega d. This is what is the second derivation. Then the third derivation is the peak time derivation. So peak time derivation means, when it is peak time means we have finding out what is known as the normalized difference between the 1 and the peak value. We are going to find out the normalized difference between this line and this line. That is peak. So this is 1 and this is peak. Okay. So you can get it equal to MP is equal to CTP into minus 1, because the time taken to reach this peak value is equal to TP. So when you put in the equation C is equal to CTP, whatever answer you get, that answer you have to subtract from 1. So if you subtract it from 1, you will get, see here, CTP minus 1 I am doing. So MP will be CTP value I will put. See, wherever T is there, I am putting TP and I am subtracting 1 from that. This one and this one cancel, so minus. So it is minus zeta omega n into TP divided by 1 minus zeta square into sine omega d. I am putting value of TP. TP is pi upon omega d. So omega d cancels, pi will remain same. So if you so omega d and omega d cancels, only pi will there. So I expand that, sine pi into cos pi plus cos pi into sine pi. So I will go on putting the value of phi, and sine pi is 0 only. So sine pi is 0 and cos pi is 1. So cos pi, only this term will come. This term will automatically become 0. So I will substitute the value of phi back into the equation. So it will become like this. That is MP, that is peak overshoot, is e to the power minus pi divided by root of 1 minus zeta square, and it will be in a fraction. So if you want in percentage, multiplied by 100. So these are the derivations. Then settling time, there is no derivation. So it is based on the experimental result. It is based on the experimental result. That is, number of experiments are carried out for different values of zeta and omega n, and from that graph following conclusion is made. So for 5% tolerance band, for 5% tolerance band, it is 4 divided by zeta omega n, and for 3% tolerance band, it is 2% tolerance band, it is 3 divided by zeta omega n. 2% tolerance band means between 98.98 to 101.02. So these are the derivations. So here we'll stop now. We'll take a break. At 11 o'clock, we'll meet back. If you have any doubts or any questions, you can ask me. You can unmute your mic or put it in the chat box. Okay, somebody, see, some person has written, explain slower. See, what you have to do is, anyway, we'll share it with you. And this is all lengthy derivation. So go through that derivation first. If you go through that derivation, then you can ask me the questions. So here, the method which is used for first order system, same method is going to be used for second order system by partial fractions. So if I start from the beginning, for second order system, See here, this is a underdamped case. It is written like this: A, B, C values. A, B, C are partial fractions. A is 1, B is minus 1, so on. C is minus zeta omega n, so on. You will get it. And that can be written like this. And then you can take the inverse Laplace. After taking the inverse Laplace, you simplify. See, it is not possible to explain it like this here. See, doing it on a board is one thing. Explaining on a PPT is a different thing. So complete derivation we have done. So go through that derivation once we share that. And if you have any questions, you can ask me. If you have a doubt, some other doubts, you can ask me. Anybody else? No. So I will take a break now and we'll meet at 11 o'clock.